In this paper, we propose a VLM-guided trajectory-conditioned diffusion policy for robust long-horizon manipulation, utilizing the state-of-the-art vision language models to decompose long-horizon tasks into concise, manageable subtasks, and generate voxel-based trajectories for each subtask to conditioning and steering the diffusion policy. Here is an overview of our proposed method. In the first part of our approach, we utilize a vision language model to decompose the task and generate corresponding trajectories. For this example, the task is to open one bottle. Initially, an image of the environment and a text prompt are fed into the VLM. Based on these inputs, the VLM identifies two subtasks: grasp the wine bottle cap and open the wine bottle. Depending on the complexity of the task, there may be more subtasks in other scenarios. Next, the initial observation image is reprojected and marked with axes as visual prompts. This, along with the subtask description, are fed back into the VLM. The VLM generates a trajectory using a voxel grid selection process. This trajectory is then transformed into a voxel-based spatial trajectory matrix for policy conditioning. Similar to the original diffusion policy, we employ a denoising diffusion probabilistic model to approximate the action distribution. In this image, you can see a typical denoising step where the diffusion policy is conditioned on both the observation and the denoising step. However, unlike the original approach, which relies solely on these two inputs, our trajectory-conditioned diffusion policy has an additional conditioning element, the trajectory. This trajectory condition is incorporated at every step, offering a more structured and precise method for action generation. These videos demonstrate the performance on R-bench tasks. The changes in the trajectory condition reflect transitions between subtasks. These are demos for long-horizon tasks. Notice the diffusion policy are hesitating when facing choices, and thus fail to complete the task, while ours can stack blocks one by one with the help of the trajectory condition. When facing different variations, our policy are also more robust compared to diffusion policy due to the additional modality, the trajectory. We also evaluate our methods in real environment setup. The results are consistent with our simulation results. These results validate the practical applicability and real-world effectiveness of our algorithm.